You were told the sky is blue because molecules scatter blue light more than red light. That's the explanation. That's what you learned. Maybe in school. Maybe from a documentary. Maybe from someone who sounded confident enough that you didn't ask further. And it sounds like an answer. It has the right shape. It uses the right words. Molecules. Scatter. Blue light. Scientific nouns. A verb that implies mechanism. A color that matches observation. But here's what you should notice. You don't actually understand it. You don't know why molecules would scatter blue more than red. You don't know what scatter means as a physical process. You don't know what property of blue light makes it more susceptible. You don't know what property of molecules makes them prefer it. You just know the sentence. And you've mistaken the sentence for understanding. This is not your fault. This is how explanations are usually given. A question is asked. A sentence is provided. The sentence contains the right technical words. Everyone nods. The discomfort goes away. But nothing has actually been explained. Feynman hated this. He called it knowing the name of something. You can know that molecules scatter blue light and still know nothing about why the sky's blue. The word scatter is doing all the work. It's a black box. You put blue light in, you get blue light out at different angles, and you never ask what happened inside the box. But the box is where the actual physics lives. The truth is that scattering is not a cause. It's a label for an effect that needs its own explanation. And when you dig into that explanation, the whole picture changes. The molecules aren't doing what you think they're doing. The light isn't doing what you think it's doing. And the sky isn't blue for the reason you think it is, not even close. So before we go any further, you need to let go of the explanation you were given. Not because it's not false, but because it's empty. It's a sentence-shaped object that blocks curiosity instead of satisfying it. The real answer is stranger, and it starts with the fact that light doesn't bounce. When you hear scatter, you picture something bouncing. A photon comes in. It hits a molecule. It ricochets off at some angle, like a ball hitting a wall. The molecule is a tiny obstacle, and blue photons, being smaller or faster or something, bounce more easily than red ones. That's the picture. And that picture is wrong. Not slightly wrong. Not incomplete. Fundamentally, architecturally wrong. Light is not a particle bouncing off a surface. Light is an electromagnetic wave. It's an oscillating electric field and an oscillating magnetic field, perpendicular to each other, rippling through space. When sunlight passes through the atmosphere, it's not a stream of bullets, it's a continuous, undulating disturbance in the electromagnetic field, and molecules are not walls. Molecules are not solid. They are not surfaces. They are not barriers that reflect things. A molecule is a collection of charged particles, electrons and nuclei, held together by electric forces. That's it. There's no stuff there, no material, just charges, and the fields they produce and the forces those fields exert. So when light passes through the atmosphere, here's what's actually happening. The oscillating electric field of the light pushes and pulls on the charged particles inside the molecules. The electrons, specifically, they're light. They're loosely bound. The electric field of the light wave shakes them. And here's the part that changes everything. When you shake a charged particle, it radiates electromagnetic waves. This is not a metaphor. This is not approximate. This is one of the foundational facts of electromagnetism. An accelerating charge produces a changing electric field, which produces a changing magnetic field, which produces a changing electric field out into space. That's light. That's what light is. So the light doesn't bounce off the molecule. The light drives the electrons in the molecule to oscillate. Now, when those oscillating electrons emit new light, light in, light out. But the light coming out is not the same light that went in. It's fresh light, generated by charges that were forced to move. This process, driving charges to shake, causing them to radiate. This is what scattering actually is. Not a ricochet, not a reflection, a two-step conversion. Absorption of the incoming wave's energy into electron motion, then re-emission of that energy as a new electromagnetic wave. The molecule becomes a tiny antenna, a secondary light source. And once you see it this way, the question changes. The question is no longer, why does blue light bounce more? The question is, why do oscillating electrons radiate blue light more strongly than red? That's the real question. And the answer requires you to understand what matter actually is. You think of matter as solid, a table, a wall, your own hand. These feel like things, continuous, substantial, made of stuff that occupies space and resists being pushed through. But that's not what matter is. Matter is not solid. Matter is not continuous. Matter is not stuff. Matter is a collection of charged particles, electrons and atomic nuclei, separated by distances that are enormous compared to their own sizes. If an atom were the size of a football stadium, the nucleus would be a marble at the center, and the electrons would be pinpricks somewhere in the outer seats. Everything else is empty space. Except it's not even empty space. It's fields. Electric fields produced by the charges. The reason matter feels solid is not because there's material there. It's because when you try to push your hand through a table, the electrons in your hand are repelled by the electrons in the table. Electric forces, field interactions. Not substance, not contact. Just charges pushing on other charges through the electromagnetic field. This is what matter is. Charges and the fields they make, and nothing else. And charges have a property you need to understand. They respond to electric fields. If you place a charged particle in an electric field, the field exerts a force on it. The particle accelerates. If the electric field oscillates, if it reverses direction periodically, the particle oscillates too. It shakes back and forth, driven by the changing field. Now, sunlight is an oscillating electric field. When sunlight passes through a molecule of air, nitrogen, oxygen, doesn't matter. The electric field of the light wave pushes on the electrons in that molecule. The electrons are bound to the nuclei, but they're not rigidly fixed. They're held by electric forces, like weights on springs. When the light's electric field oscillates, the electrons oscillate too. Not much. The amplitude is tiny. But they move, they accelerate, back and forth, hundreds of trillions of times per second, in rhythm with the passing wave. And here's the thing you need to let sink in. Every electron in every molecule in the atmosphere is doing this, right now, all the time, whenever light passes through. The air is not passive. The air is not transparent in the sense of being inert. The air is full of charges being driven to dance by the electromagnetic field of sunlight. You don't see this. You see the sky. But what you're calling the sky is actually the consequence of trillions upon trillions of electrons oscillating in response to the sun's light. Because here's what happens next. Those oscillating electrons don't just shake, they radiate. Every single one of them becomes a source of electromagnetic waves, tiny, weak, but real. And the light they emit, this secondary light, this re-radiated light, is what you see when you look up. The sky is not the sun's light reflected. The sky is not the sun's light filtered. The sky is a new light, generated by electrons that were shaken by the sun, and the color of that light depends on how hard those electrons were shaken. An accelerating charge produces light. This is not obvious, it's not intuitive, but it's one of the deep structural facts of the universe. If you take an electron or any charged particle and you accelerate it, it radiates electromagnetic waves. Always, without exception. Why? Because a moving charge produces a magnetic field. If the charge accelerates, that magnetic field changes. A changing magnetic field produces an electric field. A changing electric field produces a magnetic field. The two fields propagate outward, sustaining each other, rippling through space at the speed of light. That's what light is. That's where it comes from. Not just from hot objects or lasers or light bulbs, but from any accelerating charge anywhere, ever. An electron sitting still, no radiation. An electron moving at constant velocity, no radiation. An electron accelerating even slightly, radiation. Electromagnetic waves. Light. Now. When sunlight passes through a molecule, the oscillating electric field of the light drives the electrons to oscillate. And oscillation is acceleration. The electrons are constantly reversing direction, speeding up, slowing down, speeding up again, hundreds of trillions of times per second. So they radiate. Each electron becomes a tiny dipole antenna, broadcasting electromagnetic waves in nearly all directions. The light they emit has the same frequency as the light that drove them, because they're oscillating at that frequency. If blue light shakes them, they emit blue light. If red light shakes them, they emit red light. But here's the critical asymmetry. They don't emit with the same strength. The intensity of the radiated light, the power output of an oscillating charge, depends on how hard it's being shaken. Not just the amplitude of the oscillation, but the acceleration. An acceleration for a given driving force depends on frequency. Think about it this way. Imagine you're shaking a weight on a spring. If you shake it slowly, low frequency, the weight barely has to accelerate to keep up. It drifts back and forth, smooth and lazy. But if you shake it fast, high frequency, the weight has to reverse direction rapidly. The accelerations become violent. Same amplitude, but much higher acceleration. The same thing happens with electrons. A low-frequency wave, red light, drives the electron to oscillate gently. A high-frequency wave, blue light, drives it to oscillate frantically. The electron has to reverse direction much more quickly. The accelerations are much larger, and larger accelerations mean stronger radiation. This is where the frequency dependence comes from, and not from some mysterious property of blue photons bouncing better, not from molecular cross-sections or wavelength-to-size ratios, from the fact that high-frequency light shakes charges harder, and harder shaken charges radiate more intensely. The mathematics of this is precise. The radiated power from an oscillating dipole scales as the fourth power of the frequency. Write that down if you want. Intensity proportional to omega to the fourth power, where omega is the angular frequency of the light. Fourth power. That's steep. Blue light has a frequency about 1.7 times higher than red light. Raise that to the fourth power, nearly 10 times more intense. Blue light doesn't scatter a bit more than red. It scatters roughly 10 times more. But here's what you need to understand. This is not an empirical fact that someone measured and fit to a curve. This is a consequence of what light is and what matter is. Fields and charges. Oscillation and acceleration. Emission and re-emission. Rayleigh scattering, the technical name for this process, is not a phenomenon. It's an inevitability. It's what must happen when electromagnetic waves pass through a gas of charged particles. And the sky is blue because blue light makes electrons shake harder. You might be wondering, if all colors of light shake the electrons, why don't we see white? Why doesn't the sky just glow with every color equally, a pale, washed-out version of sunlight? Because the electrons don't respond to every color equally. Sunlight contains all visible frequencies, red, orange, yellow, green, blue, violet, mixed together in roughly similar proportions. When that light enters the atmosphere, at every frequency drives the electrons to oscillate at that frequency. Red light drives red oscillations. Blue light drives blue oscillations. Each molecule is responding to the full spectrum simultaneously, shaking at a superposition of frequencies. And each frequency causes the electrons to radiate at that same frequency, but not with the same intensity. The intensity of the re-emitted light depends on the acceleration of the electron, and the acceleration depends on the frequency of the driving wave. High frequency means rapid oscillation, means large acceleration, means strong radiation. The relationship is not linear, it's not even quadratic, it's quartic. Fourth power. Let's make this concrete. Blue light has a wavelength of about 450 nanometers. Red light has a wavelength of about 650 nanometers. Wavelength and frequency are inversely related. Shorter wavelength means higher frequency. So blue light oscillates about 1.44 times faster than red light. Now raise that to the fourth power. 1.444 is approximately 4.3. That means for the same amplitude of the incoming wave, the blue-driven oscillations produce more than 4 times the radiated power of the red-driven oscillations. And if you compare deep blue or violet, say 400 nanometers, against deep red, say 700 nanometers, the ratio becomes even more extreme. 700 over 400. 4 is approximately 9.4, nearly 10 times stronger. So when sunlight passes through the atmosphere, every molecule re-radiates the full spectrum, but the blue and violet components are radiated far more intensely than the red and orange components. This is not filtering. The red light is still there. It's still being re-emitted. It's just being re-emitted weakly. The sky is not blue because red light is removed. The sky is blue because blue light is amplified in the re-radiation process. And here's the subtlety you need to grasp. This is happening everywhere, all at once. Every molecule in the atmosphere is being driven by the sun's light. Every molecule is re-radiating. The light you see when you look at the sky is not coming from a specific place. It's coming from every point along your line of sight. From molecules 10 meters away. From molecules 10 kilometers away. The entire volume of air between you and space is glowing with re-emitted light, faint, diffuse, but real. And because the re-emitted light is dominated by high frequencies, blue and violet, the glow is blue. You might ask, why not violet? Violet oscillates even faster than blue. Shouldn't the sky be violet? It should. Physically, it nearly is. The scattering intensity peaks in the violet, but your eyes are not equally sensitive to all frequencies. Human vision is less sensitive to violet than to blue, and the sun's spectrum itself is slightly weaker in the violet than in the blue. So the combination of scattering intensity, solar spectrum, and human eye response produces the sensation you call blue. But the mechanism doesn't care about your eyes. The mechanism is purely electromagnetic. High-frequency light shakes charges harder. Harder shaken charges radiate more intensely. That's it. That's the whole story. No molecules preferring blue, no photons bouncing better, just oscillation, acceleration, and the fourth power law of dipole radiation. And when you look up and see blue, What you're actually seeing is the fact that matter is made of charges, and charges respond to fields, and the response is frequency dependent. You're seeing the infrastructure of reality. Look up. What you're seeing is not the sun's light, not directly. The sun is off to the side or behind you or overhead. The light from the sun is traveling through the atmosphere in straight lines, mostly downward toward the ground. But you're not looking at the sun. You're looking at the sky, at the blue expanse above and around you. And that light, that blue light entering your eyes, is coming from the air itself. Not reflected off the air, not filtered through the air, emitted by the air. Every molecule of nitrogen and oxygen in your line of sight is being driven to oscillate by the passing sunlight. Every oscillating electron in every one of those molecules is radiating electromagnetic waves. Faintly, weakly, but in every direction. Some of that radiation happens to be traveling toward you. It enters your eye, you see it. You call it the sky. But the sky is not an object, it's not a surface, it's not a backdrop. The sky is a volume of space filled with tiny, oscillating emitters, trillions of them per cubic centimeter, each one broadcasting light in nearly all directions. Blue light, primarily, because blue oscillations radiate more intensely. You are not seeing a thing. You are seeing a process. And here's what makes this strange. The light you're seeing was not sent to you. It was created locally, right there in the molecules your eyes happen to be pointing at. The original sunlight, the light that left the sun 8 minutes ago, most of it is still traveling downward. But a tiny fraction of its energy has been absorbed by electrons, used to drive their oscillations, and re-emitted as new light. Some of that new light is moving toward your eyes. This is what scattering is. Not deflection, re-emission. And the reason the sky looks uniform, why every direction you look appears roughly the same shade of blue, is because the process is happening everywhere. There's no special location, no central source, just a vast, diffuse cloud of re-radiators, all responding to the sun's light, all glowing faintly blue. Now think about what happens when you look at the horizon. When you look straight up, the light entering your eye has traveled through maybe 10 or 20 kilometers of atmosphere. But when you look toward the horizon, the light has traveled through hundreds of kilometers of atmosphere, because your line of sight is nearly tangent to the Earth's surface, passing through a long, shallow path of air. More air means more molecules. More molecules means more re-emitters. More re-emitters means more accumulated blue light. That's why the sky near the horizon is often paler, more washed out. The sheer amount of scattering becomes so large that even the red and green components start to contribute noticeably. The blue is diluted by the other colors, and you get a lighter, whitish blue. And here's the flip side. When you look at the sun directly, don't actually do this, but imagine it. The light entering your eye is sunlight that has passed through the atmosphere without being scattered much. Most of it traveled straight through. The blue has been partially siphoned off into other directions, re-emitted sideways by all those oscillating electrons. What's left is slightly depleted in blue, richer in red and yellow. That's why the sun looks yellowish during the day. Not because it is yellow, the sun's surface emits roughly white light, but because the blue has been stolen by the atmosphere, redirected, turned into the sky, and at sunset, when the sun is low on the horizon, the sunlight has to pass through an even thicker slab of atmosphere. More opportunities for blue light to be scattered away. By the time the light reaches your eyes, almost all the blue is gone. Only the reds and oranges remain. The sunset is red because the sky is blue. They're the same phenomenon. One is the light that got away. The other is the light that didn't. And all of it, the blue sky, the yellow sun, the red sunset, all of it comes from the same mechanism. Electrons shaking in response to electromagnetic waves, re-radiating, creating new light. The atmosphere is not a passive medium. It's an active participant. A luminous screen of oscillating charges. You are not looking through the atmosphere. You are looking at it. Feynman used to say that knowing the name of something is not the same as understanding it. He told a story once about walking in the woods with a friend as a child. The friend's father had taught him the names of birds. He'd point and say, "That's a brown-throated thrush." And he'd know the name in different languages, Italian, Portuguese, Chinese. But Feynman's point was, the boy didn't know anything about the bird. He knew labels, words, sounds people had agreed to make. But he didn't know what the bird did, or how it lived, or why its feathers had that color. The sky is blue because molecules scatter blue light. That's a label. It sounds like knowledge. It has the structure of an explanation. Subject, verb, object, cause and effect. But it's empty. It's a brown-throated thrush. What Feynman wanted, what he spent decades trying to show people, is that the real explanation is not a sentence. It's a picture, a mechanism, an understanding of what's actually happening, built from pieces you can see in your mind. Light is an oscillating electromagnetic field. Matter is made of charged particles. Oscillating fields exert forces on charges. Charges that accelerate produce electromagnetic fields. Those fields propagate as waves. The intensity of those waves depends on the frequency of the acceleration. Fourth power. Blue shakes harder than red. Blue radiates stronger than red. The sky glows blue. That's the explanation. Not because it uses fancier words, but because every step is a consequence of the previous one. You can see why each thing happens. There are no black boxes, no mysterious preferences, no words doing work they haven't earned. And here's what that explanation reveals. The sky is not blue because of some quirk of chemistry or atmospheric composition. The sky is blue because the universe is made of fields and charges, and those fields and charges obey laws that produce this exact outcome. If you built a different planet with a different atmosphere, different molecules, different densities, but still made of charged particles, the sky would still be blue, maybe a slightly different shade, maybe lighter or darker, but blue. Because the omega-4 dependence doesn't come from nitrogen or oxygen. It comes from electromagnetism itself. The color of the sky is not a fact about Earth. It's a fact about how reality works. And this is what Feynman wanted you to feel. Not comfort, but awe. Not the satisfaction of having an answer, but the vertigo of realizing that the answer reveals something deeper. Something you weren't expecting. You thought you were asking about the color of the sky, but you were actually asking why matter is transparent, why electromagnetic waves can pass through collections of charges without being absorbed entirely, why re-radiation happens at all, why the laws that govern oscillating dipoles take the form they do. And those questions don't have answers in the same way. At some point, you reach bedrock. You reach the axioms, the structure of Maxwell's equations, the fact that accelerating charges radiate, the fact that this is just how the electromagnetic field behaves. You can ask why the universe has an electromagnetic field. You can ask why it obeys Maxwell's equations and not some other set of rules. But those questions don't have answers, not yet, maybe not ever. What you have instead is this, a description, a set of laws that predict, with staggering precision, what will happen when light meets matter. And one of the things those laws predict is that if you stand on a planet with an atmosphere and look up during the day, you will see blue. Not because blue is special, not because molecules prefer it, but because high-frequency oscillations produce stronger radiation, and your eyes happen to register those frequencies as the color you call blue. The sky is blue because of math, because of fields, because of the deep, silent logic that governs how charged particles interact with light. And when you look up now, you're not seeing scattered light. You're not seeing reflected light. You're seeing the universe doing what it does. Electrons responding to fields. Fields propagating through space. Energy converting from one form to another and back again. An endless conversation between matter and radiation. That's the sky. Not a thing. A process, a consequence, a window into the rules. And the rules don't care what you find intuitive.